I keep talking about solutions to the time-independent Schrodinger equation and how they have nice mathematical properties. What that actually means is, well, what I'm referring to are the orthogonality and completeness of solutions to the time-independent Schrodinger equation. What that actually means is the topic of this lecture. To recap, first of all, these are what our stationary states look like for the infinite square well potential. This is the potential such that v of x is infinity if x is less than 0 or x is greater than a, and 0 for x in between 0 and a. So if this is our potential, you express the time-independent Schrodinger equation, you solve it, you get sine functions for your solutions. You properly apply the boundary conditions, namely that psi has to go to 0 at the ends of the interval because the potential goes to infinity there. And you get n pi over a times x as your argument to the sine functions. And you normalize them properly, you get a square root of 2 over a out front. The energies associated with these wave functions, and this energy now is the separation constant in the conversion from the time-dependent Schrodinger equation to the time-independent Schrodinger equation, are proportional to n, that index. The wave functions themselves look like sine functions, and they have an integer number of half wavelengths, or half cycles, in between 0 and a. So this orange curve, this is n equals 1. The blue curve is n equals 2. The purple curve is n equals 3. And the green curve is n equals 4. If you calculate the squared magnitude of the wave functions, they look like this. 1 hump for n equals 1. 2 humps for the blue curve, n equals 2. 3 humps for the purple curve, n equals 3. And 4 humps for the green curve, n equals 4. So you can see just by looking at these wave functions that there's a lot of symmetry. One thing we talked about in class is that these wave functions are either even or odd about the middle of the box, and this is a consequence of the potential being an even function about the middle of the box. If I draw a coordinate system here, going between 0 and a, either the wave functions have a maximum or they have a 0 at the middle of the box. So for n equals 1 we have a maximum, for n equals 2 we have a 0. And this pattern continues. The number of nodes is another property that we can think about. And this is the number of points where the wave function goes to 0. For instance, the blue curve here for n equals 2 has 1 node. This trend continues as well if I have a wave function that, for instance, let me draw it in some absurd color, has 1, 2, 3, 4, 5, 6, 7 nodes. You know this would be for n equals 8. This would be sort of like the wave function for n equals 8. These symmetry properties are nice. They help you understand what the wave function looks like, but they don't really help you calculate. What helps you calculate are the orthogonality and completeness of these wave functions. So what does it mean for two functions to be orthogonal? Let's reason at this from a perspective which you're more familiar, the orthogonality of vectors. We say two vectors are orthogonal if they're at 90 degrees to each other, for instance. So if I had a two-dimensional coordinate system, and one vector pointing in this direction, let's call that A, and another vector pointing in this direction, let's call that B, I would say those two vectors are orthogonal if they have a 90-degree angle separating them. Now that's all well and good in 2 dimensions. It gets a little harder to visualize in 3 dimensions, and, well, what does it mean for two vectors to be separated by 90 degrees if you're talking about a 17-dimensional space? In higher dimensions like that, it's more convenient to define orthogonality in terms of the dot product. And we say two vectors are orthogonal in that case if the dot product of those two vectors is 0. Now in 2 dimensions, you know the dot product is given by the x components of both vectors, ax times bx, plus the y component of those two vectors multiplied together, ay times by. If this is 0, we say these two vectors are orthogonal. In 3 dimensions, we can say plus az times bz. And if this is equal to 0, we say the vectors are orthogonal. And you can continue this, multiplying together like components, or same dimension of the components of vectors in each dimension, multiplying them together. A1, B1, A2, B2, A3, B3, A4, B4, all added up together. And if this number is 0, we say the vectors are orthogonal. We can extend this notion to functions. But what does it mean to multiply two functions like this? In the case of vectors, we were multiplying like components, both x components, both y components, both z components. In the case of functions, we can multiply both functions' values at particular x coordinates and add all those up. And what that ends up looking like is an integral. Say the integral of f of x, g of x, dx. So I'm scanning over all values of x instead of scanning over all dimensions, and I'm multiplying the function values at each individual point, at each individual x, together, and adding them all up, instead of multiplying the components of each vector together at each individual dimension and adding them all up. The overall concept is the same, and you can think about this as, in some sense, a dot product of two functions. Now, in quantum mechanics, since we're working with complex functions, it turns out that we need to put a complex conjugate here on f in order for things to make sense. This should start to look familiar now. You've seen expressions like the integral of psi star of x times psi of x dx is equal to 1, our normalization condition. This is essentially the dot product of psi with itself. Psi, of course, is not orthogonal to itself, but it is possible to make a pair of functions that are orthogonal. And we say functions are orthogonal if orthogonal, if and only if the integral over the domain of the functions now, which I'm leaving off, there are limits on this integral, but I'm leaving them off, f star of x, g of x, dx is equal to 0. As a brief side note here, we can also make a connection with the magnitude of a vector, or the norm. For instance, we say if a vector dot a vector is equal to 1, we call this a unit vector. And in the case of functions like this, if, for instance, the integral of psi star psi dx is equal to 1, then we say psi is normalized. So both of these concepts, like dot products and unit vectors, dot products and normalized functions, or inner products of functions, you may hear that term as well, can be generalized. Orthogonality turns out to be really useful because integrals like this appear a lot in quantum mechanics, and it's very handy when we can look at an integral and say, oh, it's 0. In the case of the particle in a box, or the infinite square well potential, we got sine functions. So what does this actually look like in real life? Well, sine functions obey an orthogonality condition, and this is the orthogonality integral. Now I'm just going between 0 and a, and I have the sine of n pi over a times x, sine of m pi over a times x. And right now I'm going to stipulate that m is not equal to m. m is not equal to n. You'll see where this comes in later. This integral can be done reasonably easily if you remember your trig identities. And I certainly don't remember my trig identities. I have to go and look them up all the time. But sine of x times sine of y, this is a product identity for sine, is equal to 1/2 of cosine x minus y minus the cosine of x plus y. If you apply this identity to this product, what you end up with is a half out front, the integral from 0 to a, as before, and now we have two cosine terms. And we're going to have a cosine of n minus m pi x over a plus cosine of n plus m pi x over a, all integrated dx. This is now an integral you can do. It's just an integral of cosine. And what you get If n is not equal to m, this term is non-zero, this term is non-zero. Both of these just work out fine. And we end up with, for our integral, where did it go? A half out front, as before, a over n minus m pi times the sine of n minus m pi x over a plus, is there a plus? Sorry, I've gotten the sign backwards here. This sign should be minus, same as this sign. The sign should be minus here as well. A over n plus m pi sine n plus m pi x over a. And this whole thing is evaluated between 0 and a. Now, I can do the evaluations. If I plug in a for this, I'm going to be plugging in an a here for this x. So the a's are going to cancel, and I'm just going to be left with n minus m pi. This is going to be a half, ugly half, going to be a half of, actually let's pull the a out front, since I have an a here and an a here. Let's pull the pi out front as well. So I've got a over 2 pi out front, and then I'm going to have sine of n minus m pi over n minus m minus the sine of n plus m pi over n plus m. This is evaluated at a, and if I evaluate it at 0, well, I get 0. Because if I substitute 0 in for x here or 0 in for x here, the whole argument of sine is 0, and sine of 0 is 0. So this is our answer. But we know that sine of n and m both being integers, the sine of an integer times pi is also 0. So these are 0 as well. The sine term here goes to 0, the sine term here goes to 0. And what we're left with is just 0. Which means, subject to our assumption that m is not equal to m, the sine of n and m, these two sine functions of n pi x over a and n m pi x over a, are orthogonal. In the case of normalized wave functions, these constants out here end up canceling out, and what you end up with is the integral of psi star psi, I'll write out the dependence, the integral of psi sub n star of x and psi sub m star of x, integral dx. Now the integral is from 0 to a, is equal to, I'm going to write this in terms of something called the Schrodinger delta, delta mn, where delta mn is defined to be 1 if m equals n, and 0 if m is not equal to n. So these are the sort of orthogonality conditions we'll be working with in quantum mechanics, and writing them out in terms of the Schrodinger delta is a handy way of doing things. That's what orthogonality actually looks like for the solutions to the time-independent Schrodinger equation for the infinite square well potential, the particle in a box. If I move forwards a little bit, where are we going with this? These orthogonality conditions are really handy, thanks to something called Fourier's trick, what your textbook, what Griffiths calls Fourier's trick. And the trick goes like this. Suppose I have some general function of x. I'm going to hypothetically say I'm going to write this function f of x as an infinite sum of constants multiplied by sine functions. If this were possible, how would I find the Cn, C sub n, necessary to write this? And it turns out that you can do this pretty easily. What you do is take f of x, which is equal to the sum over n equals 1 to infinity of C sub n sine n pi x over a, and from the left I'm going to integrate both equations, but before I integrate them I'm going to multiply them by sine m pi x over a sine m pi x over a. And these are both integrals dx, which I can make some space for. So I'm taking this original equation and I'm multiplying it from the left by sine m pi x over a, and I'm integrating from 0 to a dx, both sides of this equation. If I do this, there's not much I can do with the left side since I don't know what f of x is, but I can work with the right-hand side. So let's look at the right-hand side here. The right-hand side, first thing I'm going to do is I'm going to exchange the order of summation and integration, and I'm going to pull the constant c sub n out of the integral. So what I have on the far left then is the sum from n equals 1 to infinity, c sub n times the integral of from 0 to a of sine m pi x over a times this sine n pi x over a dx. Now, you know what this integral looks like. This looks like the orthogonality condition we were working with on the last page. So it turns out this is going to be equal to 0 if n is not equal to m. So if you imagine this sum as being this term repeated over and over and over again for different values of n, all of those terms are going to vanish except for the one term when n equals m. So what that means is that we no longer have a sum here, we have only a single term, and that single term is given by Cm, integral from 0 to a, of sine of m pi x over a times the sine of m pi x over a, since n is now equal to m. So I'm just going to write this as sine squared dx. And this looks like our normalization condition. We know how to do this integral. This just comes out to a over 2. So we've done all of our integrals and we've made our sum go away, which is a pretty neat trick. We have our left-hand side over here, and our right-hand side is just Cm times a over 2. So we can solve for Cm, and what you get is that Cm is equal to 2 over a times the integral from 0 to a of f of x sine m pi x over a dx. This tells us that if this is possible, to write f of x as a sum like this, it gives us a formula for what numbers to use in the sum. So that's all well and good. But does that actually work? This is nice because it allows us, or it hypothetically allows us to express any function. In the context of the Schrodinger equation, this would be any initial conditions to the Schrodinger equation. And it allows us to express that as a sum of, these are now going to be our stationary states. So our initial conditions maybe we can express them as a sum of stationary states. You know, superpositions of stationary states are also solutions to the Schrodinger equation. So this is good. It allows us to construct whatever sort of wave function we want in terms of the functions that we have. If we follow this formula, maybe it will work. Does it work? That's the other property that's really nice about solutions to the time-independent Schrodinger equation. They form what's called a complete basis. They are a complete basis set. This is like having a set of unit vectors with which you can express any other unit vector. For instance, x hat, y hat, and z hat. Unit vectors pointing in the x, y, and z directions form a basis for 3D space. If we have a set of solutions to the Schrodinger equation, for instance, the solutions to the Schrodinger equation for the infinite square well potential, our sine function, they actually form a complete basis for functions. Which means this formula for expressing some function f of x in terms of a sum of sine functions, where the numbers used in the sum are calculated by this Fourier's trick sort of integral, this actually works for damn near any f of x. Not quite any, just for the sake of being mathematically rigorous, this is really only going to work for smooth square integrable functions. Eesh. If f of x blows up to infinity, this isn't going to work. And if f of x has a lot of corners and discontinuities, this isn't going to work either. But for smooth square integrable functions, which happens to be what we really care about for quantum mechanics, this works. How does this actually work out? Why does this actually work out? Just to say very briefly, conceptually, how this works. This works because it is possible to write sum of c sub n sine of n pi x over a, such that if I plotted this as a function of x between 0 and a, I can make functions that look like this. I can make functions that are very sharp and very tall. And I can make these functions wherever I want by suitable choices of this Cn. So if I change Cn, I can change the position of this spike. And I can make this spike as sharp as I want, and I can make it as tall or as short as I want. And what that means is I can make whatever function you want. For instance, suppose the function you want looks something like this. I can make it by adding up a bunch of spikes. I can have a little spike here, and a little spike here, and a little spike here, a little spike here, etc. If I effectively fill this whole space with these very sharp spikes going up to the value of the function, I can recreate whatever function you want, no matter what shape it is. Provided it's reasonably well behaved and square integrable, this actually works really well. What this looks like graphically is shown here. This is some hypothetical f of x. F of x is shown in black now, and it runs from down here to up here. It's just a straight line. Now, if I only include the first term in this long sum, remember now we're expressing f of x as the sum of n equals 1 to infinity of c sub n times sine of n pi x over a. If I only let the sum go from n equals 1 to 1, I get the blue curve here. So there's only one term in this sum, you just get a sinusoid. It's not a very good approximation to the straight black curve. But if I let n become larger, in this case I think I have n equals 20 here for the purple curve, you can see the purple curve drops very rapidly, wiggles, but is mostly going straight along the black curve. It's having some difficulty matching the black curve at the endpoints here, and that's because part of this assumption here that we're working with sine functions, these are from the solutions to the Schrodinger equation, not from a rigorous treatment of Fourier series or Fourier expansions of functions. So since we're requiring our purple curve here to go through 0, of course it's going to have to give up on fitting the function near the endpoints. But if you include a lot of terms in this, you can make this approximation quite good. Generally, the more terms you add, the closer you get to your function. So, to sum up, the solutions to the time-independent Schrodinger equation for the particle in a box are these sine functions, and these sine functions obey an orthogonality condition. And that orthogonality condition allows you to find out relatively easily what constants to use in an expression of any function as a sum of sine functions, as a sum of stationary states. So if we have some initial conditions for our wave function, we can express it as a sum of stationary states. We then know the way stationary states evolve with time. We know then everything about how our wave function will evolve forwards in time. To check your understanding, here are two relatively straightforward problems to use Fourier's trick and the orthogonality conditions for sine to determine, for instance, C2, C3, and C4 for this f of x, or C2 for this f of x. The potential being an even function about the middle of the box. If I draw a coordinate system here, going between 0 and a, either the wave functions have a maximum, or they have a 0 at the middle of the box. So for n equals 1, we have a maximum. For n equals 2, we have a 0. And this pattern continues. The number of nodes is another property that we can think about. And this is the number of points where the wave function goes to 0. For instance, the blue curve here for n equals 2 has 1 node. This trend continues as well if I have a wave function that, for instance, let me draw it in some absurd color, has 1, 2 cycles in between 0 and a. So this orange curve, this is n equals 1. The blue curve is n equals 2. The purple curve is n equals 3. And the green curve is n equals 4. If you calculate the squared magnitude of the wave functions, they look like this. 1 hump for n equals 1. 2 humps for the blue curve, n equals 2. 3 humps for the purple curve, n equals 3. And 4 humps for the green curve, n equals 4. So you can see just by looking at these wave functions that there's a lot of symmetry. One thing we talked about in class is that these wave functions are either even or odd about the middle of the box, and this is a consequence of you express the time-independent Schrodinger equation, you solve it, you get sine functions for your solutions, you properly apply the boundary conditions, namely that psi has to go to 0 at the ends of the interval because the potential goes to infinity there, and you get n pi over a times x as your argument to the sine functions. And you normalize them properly, you get a square root of 2 over a out front. The energies associated with these wave functions, and this energy now is the separation constant in the conversion from the time-dependent Schrodinger equation to the time-independent Schrodinger equation, are proportional to n, that index. The wave functions themselves look like sine functions, and they have an integer number of half wavelengths, or half cycles. I keep talking about solutions to the time-independent Schrodinger equation and how they have nice mathematical properties. What that actually means is, well, what I'm referring to are the orthogonality and completeness of solutions to the time-independent Schrodinger equation. What that actually means is the topic of this lecture. To recap, first of all, these are what our stationary states look like for the infinite square well potential. This is the potential such that v of x is infinity if x is less than 0 or x is greater than a, and 0 for x in between 0 and a. So if this is our potential, 2, 3, 4, 5, 6, 7 nodes, you know this would be for n equals 8. This would be sort of like the wave function for n equals 8. These symmetry properties are nice. They help you understand what the wave function looks like, but they don't really help you calculate. What helps you calculate are the orthogonality and completeness of these wave functions. So what does it mean for two functions to be orthogonal? Let's reason at this from a perspective which you're more familiar, the orthogonality of vectors. We say two vectors are orthogonal if they're at 90 degrees to each other, for instance. So if I had a two-dimensional coordinate system, and one vector pointing in this direction, let's call that A, and another vector pointing in this direction, let's call that B.